Hello everyone, we are from group 2, which consists of me, Divya, Darshana, EILEEN and Jasmine. We'll be conducting experiment 2, which is the flow measurement. As for the introduction, the flow measurement is used to assist in analyzing the system in terms of consumption and leak detection and enables to reduce the energy consumption and cost. The, the, the previous slide. The objective of conducting this experiment is to compare the discharge coefficient of three types of flow measurement method, which is orifice plate, nozzle, and venturimeter. These are the apparatus I used to conduct the experiment, where the manometer, the multi-tube manometer, is used to measure differential pressure between inlet and outlet of the flow meters. The rotameter is used to obtain the actual flow rate of water, and the water is the fluid flowing medium. As for the summary of the experiment 2, is this experiment was done to determine and compare the coefficient of discharge for a series of flow measurement devices. This experiment was performed using some typical flow meters, which are orifice plate, nozzle, and venturimeter. By using these flow meters, the volumetric flow rate of the water could be calculated using the Bernoulli equation. In this experiment, the relationship between flow rate and pressure difference were formulated. Throughout the experiment, it was found that as the flow rate increases, the velocity will increase, hence the pressure will decrease. Based on the data obtained, coefficient of discharge can be calculated using the formula of actual flow rate over theoretical volumetric flow rate. Based on the experiment result, venturimeter gives more accurate measurement because its coefficient of discharge is higher compared to orifice meter and nozzle.
So I'm going to talk about the theory of this experiment. The first one, we have orifice plate. An orifice plate is a restriction with an opening smaller than the pipe diameter, which is inserted in the pipe as depicted in figure 2. Due to the smaller opening area, the fluid velocity will increase and hence causing a decrease in pressure. The flow rate can be calculated from the measured pressure drop across the orifice plate from P1 to P2. The orifice plate is the most commonly used flow sensor, but it creates a rather large non-recoverable pressure due to the turbulence around the plate, leading to high energy consumption. Figure 1 showing the schematic representation of orifice plate. Referring to figure 1, the Bernoulli equation can be applied with the assumptions of the flow that is horizontal, Z1 equals to Z2, steady, inviscid, and incompressible between points 1 and points 1 and 2. The equations for theoretical flow rate, QTH, can be expressed as the following. QTH equals to A2 over 2 in bracket times pressure difference over density in bracket 1 minus in bracket area 2 over area 1 in bracket square, where P1 minus P2 is actually equals to density times gravity times in bracket height difference. Thus, QTH equals to A2 square root 2GH times difference in height over 1 minus a 1 minus in bracket a over 2 a2 over a1 in bracket square. The coefficient of discharge CD is equals to Q actual over Q theoretical, where QTH is actually the theoretical flow rate, Q actual is the actual flow rate, A1 is internal cross-sectional area of pipe, A2 is cross-sectional area of orifice plate, P1 minus P2 is the differential pressure between point 1 and point 2, rho is the density of water, H1 minus H2 equals to differential height in manometer between points 1 and 2. G is the gravity constant, which is 9.81 meter over S squared. The second one, we have nozzle. The nozzle applied the same principle and calculation as orifice plate in 1, which with only changes on A2, the cross-sectional area of nozzle. The difference between them is only the shape of the restricted opening, whereby the nozzle, as shown in figure 2, is approximately a quarter ellipse. Last one, we have venturi. The venturi consists of rapidly converging section, denoted as point 2 in figure 3, which increases the velocity of flow and hence reduces the pressure. It then returns to the original dimensions of the pipe by a gently the diverging diffuser. By measuring the pressure differences, the discharge coefficient can be calculated. This is a particularly accurate method of flow measurement as energy loss is very small. Same principle and calculation of equation 1 to equation 3 that we have seen just now. It is same as orifice plate in 1 applied to the venturi with only changes on the A2, which is the cross-sectional area of venturi. Now I will pass to the next person to present about the methodology.
As step 1, the orifice plate is ensured that it is properly fixed at its positions and the manometer tubes H1 and H2 is fastened to the orifice plate. Then the main switch and the pump is turned off. Simultaneously, the flow control and gate valves are slowly opened until they reach their maximum opening level. Then the blade ventilation valve is opened by turning it to anti-clockwise directions to release all the bubbles in the system. Then the blade ventilation valve and gate valve are closed. The pump is turned off. The white ventilation valve is slowly opened until the minimum water level of 30 until 40 mm is reached, and then the pump is turned on. Next, the gate valve is slowly opened until the water level in H1 reached the maximum 390 mm and manometer H2 is at maximum level. The reading for manometer H1 and H2 and rotate meter Q actual for measuring the actual flow rate are recorded. The all readings are recorded for 5 different values of flow rate, actual flow rate by adjusting the opening of gate valve. The gate valve is closed and the pump is turned off. The manometer tubes H1 and H2 is removed from the orifice plate. The orifice plate is changed with nozzle and repeat the step 1 to 9. Meanwhile, for the venturi, the manometer tubes are connected to H1 and H3 and similar step 1 to 9 are applied. After finish, the manometer tubes are removed from system. The flow control valve is closed and make sure that the pump and main switch is turned off. So I will pass to the DIVIYA for explaining about the raw data analysis. Okay, as for the raw data, for nozzle, orifice plate, and venturi meter, the 3 of the flow meters are use the same data for use the same data. As for the Q rotameter, which is actually the flow rate of rotameter in unit of liter per hour. So we need to convert the liter per hour to meter cube over second to get the actual flow rate. And then the QTH, which is the theoretical volumetric flow rate, is calculated using the formula where Jasmine explained in her part, which is the equation 2. The H1 and H2 is the height that obtained from the multi-tube manometer, and the delta H is the difference between H2 and H1, where the formula is H2 minus H1. And the CD is the discharge coefficient calculated using the equation 3. Next.
Hi, so I will be talking about the data and discussion. So the first table we see is the data for orifice plate. What is obvious is as the flow rate increases, H1 increases as well, but for H2, the value decreases. Next data for nozzle. It is also, you can also see that as your flow rate increases, your H1 value increases as well, but your H2 value decreases. And then finally, for orifice plate, for venturimeter, the same trend can be seen here also. As your flow rate increases, your Q rotameter increases, your H1 increases as well, but your H3 decreases. Next for discussion. So the first thing we'll be discussing is the differences on water level in tube H1 and H2 in manometer with different types of flow meters and relate the results with pressure losses associated with types of flow meter. First, as flow rate of water increases, H1 decreases. The increase in the change in the difference of both H1 and H2 is the result of the decrease in area from section 1 to section 2. The change of water level is most significant during the observation of venturimeter, as changing of area of venturimeter is the largest, which is area of venturimeter is relatively huge compared to nozzle and orifice plate, which causes the drop of pressure due to head loss. The flow of water is horizontal, hence your displacement 1 and displacement 2 are equal and assumed steady, inviscid, and incompressible between sections 1 and 2. Your Bernoulli's equation becomes, as you can see on the screen, assuming velocity profile at both sections are uniform, our continuity equation also becomes Q equals to area 1 and velocity 1 equals to area 2 and velocity 2. As the mass flow in closed pipe is constant, when area of pipe decreases, the velocity of water flow in pipe increases, resulting in pressure drop. When this theory is applied in Bernoulli's equation, it can be concluded that the pressure is higher at pipe section with bigger area compared to section with smaller area, resulting in higher velocity. To simplify, your A2 is smaller than A1, which causes your velocity to be higher than your velocity 1 due to pressure 2 being lesser than pressure 1. So it can be concluded that your height 2 will be smaller than your height 1. Right? Now we'll be discussing about your the discharge coefficient and ranking of flow meter according to accuracy. We will, since we have calculated the discharge coefficient from the five data collected, we calculate an average we calculate an average discharge coefficient, which is 0.684 for orifice plate, 1.054 for nozzle and 0.96 for venturimeter. Next. When sudden change in diameter occurs in the piping system, there will be a pressure drop, and when the changing of cross-sectional area is bigger, the steeper the drop of the pressure. This results in the nozzle having the largest average coefficient of discharge compared to orifice plate, while venturimeter had the smallest coefficient of discharge. The flow meter that gives most accurate measurement is venturimeter. Average coefficient discharge for venturimeter is 0.96, which is the closest to 1 compared to nozzle plate and orifice plate. The accuracy of flow rate can be seen that the venturimeter has the highest accuracy, followed by the nozzle, and then lastly the orifice plate. Next. Potential errors in experiment and ways to overcome. First, the fluctuating of the flow rate makes it difficult to set up the flow rate of water to be constant, especially when we need a constant value of volume water collected at 3 liters. The start of timekeeping was not synchronized and might not be functionally clicked when the water level of tank reaches optimal height due to limitation in the time response argument. Parallax error occurs when reading the water tank level due to restrictions like height of the reader, as some may be too short or otherwise. Another form of parallax error is the observer's eyes not being perpendicular to the scale, which could lead to inaccurate measurement recorded. Lastly, presence of air bubble in the apparatus could also be a form of error present during the experiment as it affects the reading of the height of the manometer. Ways to overcome said errors. The problem of taking a constant 3-liter volume of water can be overcome by taking approximately 3 liters and measure it using a relatively more sensitive instrument, for example, a measuring cylinder. In addition to this, flow rate of water must always be constant throughout the experiment by ensuring valve is open the entire time. To reduce the parallax error, make sure that the water level is parallel with your eyes. Parallax error can also be minimized by putting a blank white paper behind the manometer to enable the meniscus of water to be viewed more clearly. To increase the accuracy of time, use digital stopwatch rather than analog stopwatch or other methods. Lastly, make sure the air bubbles in flexible tube is completely null to give the most precise reading. That's all for my part.
Based on for the conclusions, based on the data obtained, we can conclude that the venturimeter is more accurate measurements than orifice plate and nozzle, as the average discharge coefficient CD of venturimeter is 0.96, which is approximately to 1. So for the average CD for nozzle is 1.054, is more than 1, and orifice plate is 0.684, which are less than 1. So both are less accurate than the venturimeter. The difference in CD value among the flow meters is due to the structure of flow meters. When sudden change of diameter in the flow meter structure, there will be a pressure drop. So we need to avoid the parallel error by ensuring the eyes are parallel with water level to get accurate measurements. Runoff error also causes the difference in answers. So we need to repeat the calculations to get the accurate answer. So according to the continuity equations and Bernoulli's equations, the relationship between flow rate and pressure is when flow rate increases, the velocity will increase and then resulting in decreases in pressure. So that's all from group 2. Thank you.